Hello everyone. In this video, we are going to relate the continuous insurance, the discrete insurance payable at the end of the year of death, as well as the monthly insurance. Here, we not only relate the whole life insurance, this also applies to term insurance as well as deferred insurance. In this video, we will use the UDD assumption for the relationship. More specifically, we would like to approximate the continuous insurance as well as the monthly insurance from the discrete insurance payable at the end of the year of death. The reason is we are usually given a life table and the corresponding values only applies to integer ages. To approximate the continuous insurance or the monthly insurance, we may need the survival function or the whole function for the cause of mortality. However, this may not be provided. To do the approximation, first of all, we assume that there is no endowment component. That is, we do not include the endowment insurance for the time being. How do we do the approximation? One convenient way is to use the UDD assumption for fractional ages. Under the UDD assumption, A bar x is approximately equals to I over delta times AX. And for the monthly insurance, this is approximately equals to I over IM times AX. And we can get AX from the life table. And this approximation, the value is exact under UDD. Let's take a look at an illustration. First of all, using this life table, okay, make sure that the interest rate is 5%. And suppose we have the value A25, which is 0.06147. Assume UDD, we can approximate A bar 25 and A25 with bracket 4 payable at the end of the quarter of death. All right, A bar 25, we can use the approximation I over delta A25. I is 0.05, and we can get delta, which equals to the lateral log of 1 plus I, and then times A25. Upon calculation, we get the answer. This is the approximated value. And then for A25 quarterly payment, the approximation is I over I4, A25. And then we have the relationship. Upon calculation, we get 0.06261. To get the value for I over delta and over I over I4, we can make use of the table given in the exam. This interest function is evaluated at the interest rate I equals to 5%. So make sure the interest rate is 5% in order to make use of this table. All right, I over delta. We focus on this column. This corresponds to M approaching infinity. And here we get 1.0248. And this value is the approximation of 0.05 over the lateral log of 1.05. And then the second one, I over I bracket 4. This value is the approximation of this expression. All right, another illustration. Assume UDD. The approximation also applies to the second moment. That is, the second moment, A bar X, is approximately equals to the pre-superscript 2 and then I. So this is the value of the interest rate I evaluated at the double force of interest. And then over 2 delta, and then the second moment, AX. E to the power 2 delta equals to 1 plus I squared, and then we can get the pre-superscript 2I equals to this, which equals to 2I plus I squared. And therefore, this expression can be rewritten as 2I plus I squared over 2 delta, and then times the second moment, AX. This also applies to the nth insurance. Let I equals to 5%, and then get back to 825, the second moment here, 0.00788. And then we want to approximate the second moment, A bar 25. I is 0.05, pre-superscript 2I. The interest rate at the double force of interest is given by 2I plus I squared, and then over 2 delta. And we get 0.00828. For the second moment of the insurance, 825, death benefit payable at the end of the quarter of death, we have this expression. And then from the relationship, we can get the pre-superscript 2 I bracket 4. And upon calculation, we get a value 0.00818. All right, so if we do not consider endowment insurance, that is no endowment component in the policy, under UDD, AX bar equals I over delta AX. And then for the nth insurance, this equals to I over IM AX. The relationship applies to the n-year term insurance. This also applies to the deferred insurance as well. And this approximation or this relationship also applies to annually increasing, decreasing insurances. That is, we have IA by X under UDD equals to I over delta IAX, and the corresponding n-year term increasing insurance, as well as the n-year term decreasing insurance. Let's take a look at an example. For a 2-year term insurance of 1 on an individual at age 22, death benefit is payable at the moment of death. You are given that the mortality follows the given table on the right-hand side. Deaths are uniformly distributed over each year of age. The interest rate is 6%. Calculate the variance of Z. Z is the present value random variable for this insurance. All right, we are given it UDD, so we can use this relationship. We need to get the 2-year term insurance, the discrete case, payable at the end of the year of death. The first term, the present value, okay, 1 over 1.06 if the individual dies before reaching age 23. So the probability here is Q22. And then the second term, the individual dies before reaching age 24, but after age 23. The present value is the square of 1 over 1.06. Survive in the first year from age 22 to age 23, we have P22, 1 minus Q22. And then death in the following year times Q23. Upon calculation, we get the expected present value. The second moment, similar expression, except that we have the square of the present value. And then we get the second moment. And then from the relationship under UDD, the expected value of Z, this equals to I over delta, and then the 2-year term insurance for the discrete case. I is 0.06. We can get delta, the lateral log of 1.06, and then times the 2-year term insurance, the discrete case, and we get the expected value of Z. The second moment, we have this relationship under UDD. All right, we get the first and the second moment. We can compute the variance of Z. And we get the answer, 0.00046. All right, get back to the relationship. Suppose we are working with endowment insurance. That is the insurance with endowment component. Remember that this relationship does not hold. Instead, we do the approximation for the first part without the endowment component, and then we add the endowment component, the NEX. And this is the full relationship for insurance with endowment components. For the Anthony insurance, we have this relationship. We separately add the endowment component, the NEX. This also applies to the annually increasing insurance. For the annually increasing insurance, the endowment component occurs at year end, and the survival benefit is N. And therefore, the present value for this is N times NEX. For annually decreasing insurance, by the end of the N-year term period, the survival benefit is what? So we have 1 times NEX, which is simply NEX. An illustration. Suppose the mortality follows the life table given here, and assume that the interest rate is 5%. Deaths are uniformly distributed over each year of age. Calculate the 10-year endowment insurance for the continuous case at age 65. All right, we have this relationship. We need to get 10-year 65. 10-year 65 is given in this column. We need to get the 10-year term insurance. Make use of the relationship here endowment insurance equals to the expected present value of the 10-year term insurance plus 10E65, the present value of the endowment component. We can get the value for the 10-year endowment insurance along this column, 0.6265, and then 10E65 is given as 0.55305. And we can get the 10-year term insurance. Plug this into the expression with I equals to 0.05. We have the delta lateral log of 1.05, and then times the 10-year term insurance, the second term, 10E65, and we get the answer, 0.62832. Another example, given that deaths are uniformly distributed over each year of age, and you are given the following probabilities, Q40, Q41, Q42, and interest rate I is 0.08. Calculate the 3-year term annually increasing insurance at age 40. All right, make use of the relationship here. We have annuals 3, X is 40. The discrete case. The first term, death benefit is 1, the present value factor 1 over 1.08, and the probability of death within this year, 0.02, which is Q40. The second term, death benefit is 2, the present value factor, and the probability of death within this year, P40 times Q41. And then the third term, the endowment component, 3 times 3E40, we get its value. 3P40 equals P40 times P41 times P42. We get all the quantities, and we can do the calculation. I is 8%, 0.08. And then we get the answer, 2.339972. That's it for today's video. Thank you for watching, and see you in the next video.